So this section, there was a whole bunch of these trig integral type things. And the reason that your textbook is dedicated an entire section to this on its own is because of the next section, which is coming up, which is the actual trig substitution stuff, where we're going to be doing a whole different kind of substitution. All right, so that being said, did any of you try to do that? I must have put it up here somewhere. So here's how you do the secant integral. And then it was this one I wanted you to try. So if you haven't done it yet, you should give it a shot and see what you come up with. Now, the reason I'm saying this is because when you check your answer in the table of integrals, it's probably not going to be what you have. Now, this is going to happen from time to time. Depending on what direction you go, you might look at your answer and it's logarithms and shit. And you look in the table of integrals or back of the book, or you look at what the solution is and you see a bunch of hyperbolic functions and you're like, what the hell? So there's sometimes, identities. There are identities relating those inverse hyperbolics with logarithms, so might as well be aware of that. Okay, so new page. Text mode. (20822). And here we are. Are any of you planning to not show up in person on Tuesday?
I'm considering. My bed looking cozy.
Yeah. I did manage to get to the Apple store, so I have a new Apple Pencil. I'm not using it yet. All right. Well, before we move on to anything new, let's do a reality check here. The integral of dx over cosine x minus 1. Now, for you guys that are biology majors planning on going to med school or econ majors, you're probably not going to be needing to know how to integrate stuff. But, there's usually a good chunk of you that are engineering majors. And so you definitely need to get good at this, because I think after you take this class, you're at least at a university, you're supposed to go into vector statics and vector dynamics. We do have a vector statics course. Saeed was supposed to develop a dynamics course because these are sophomore level courses, but he got all involved with self-paced. And so anyways, Maybe I'll ask Tara about that or something. Okay, so what do you want to do with this guy? Any ideas?
Substitution, or separating the dx, like dx over cosine x minus dx over negative. Oh no, man. It's always like that.
We cannot do this. I did this once when I was a sophomore. I remember Professor Banks. It was just a brain fart that I had. He goes, the British accent. He said, "Oh, you just lost your license to practice mathematics." Okay, so can't do any of that shit. Okay, so there isn't any obvious thing here. Like, for example, if there was, like if there was like a sine x sitting up here, then obviously, we would do u as sine and du as cosine. Well, let's see here. Let's think about some identities. We know that sine squared x is equal to 1/2 minus 1/2 the cosine of 2x, right? So that means that 2 sine squared x equals 1 minus the cosine of 2x. So that means that cosine of 2x minus 1 equals negative 2 sine squared x. So that means that the cosine of x minus 1 is equal to negative 2 sine squared of x over 2. So now notice that we haven't done any calculus. This is just a bunch of manipulation, right? So the integral, if we want to proceed this way, would be the integral of dx over negative 2 sine squared of x over 2, which is negative 1/2 the integral of cosecant squared of x over 2 dx. Okay, now the derivative of tan is secant squared, right? So the derivative of cotan of u is negative cosecant squared u, and then the u prime. Okay, so what this is, I believe this is just the cotangent of x over 2. Because the derivative of that is going to be negative cosecant squared times the whatever. Any of you guys get that?
Nope.
Nope. Okay. Maybe there's another way to proceed. Let's try another way. I can remember coming back to school the next day after working on physics problems all night long and blah, blah, blah. And going into Professor Siegel's office, and he'd just start working out the integral on a totally different path than me. And I'm like, wait a minute, what? Now, we'd arrive at, if I did things correctly, at the same spot. But anyways, maybe we can try this, like cosine x plus 1. Did any of you think to try this? This sometimes is a knee-jerk reaction to try. So let's see, this is going to be the cosine of x plus 1 divided by cosine squared x minus 1 dx. And so that is cosine x plus 1. And then this is going to be negative sine squared x dx. Okay, so now we can break it into two integrals. Equals negative cosine x over sine squared x dx minus the integral of cosecant squared of x. Okay, now look at this is kind of a far cry from that thing. All right.
Sorry, but how did you get to integral of cosecant square x?
Isn't 1 over sine squared cosecant squared?
Oh, okay, I see.
Yeah. Okay, so depending on what kind of mood we're all in when we get done with this, maybe we'll track this around and try to see if we can. First of all, did I make any errors here?
No, you're good.
I think the derivative of this is this, and that is the same as that, as long as I didn't mess it up. Okay, so here, I think what we would do is we would have u equaling sine x, and so then du would be cosine x, right? dx, like so. And so this is going to be negative integral of u to the negative 2 du. And then this is going to be the cotangent of x. And then there's going to be this constant c hanging around. So this is going to be u to the negative 1 over negative 1. So that's going to be 1 over sine of x, which is the cosecant of x, plus the cotangent of x. Huh, that's interesting. Did I make any mistakes there? I'm not trying to. By the way, this is where it's better to have the board because I'm sure I can split the screen here. I just haven't figured out how to do it. By the time class is over, I'm more interested in starting to work out and less interested in figuring out how to split the screen. And then the day rolls on and I end up not learning how to split the screen. Okay, so same problem, two different solution methods. Okay, now let's do something here.
Professor, I have a question.
Yeah.
How does cotan x stay cotan x at the end?
Well, isn't the derivative of cotangent negative cosecant squared x?
Yes.
So there's negative cosecant squared x. How about this? Plus negative.
Okay, thank you.
All right. Okay, now, if you bear with me for a second, somewhere in here, I have the solution manual. Let's see how the solution manual reported it. Single variable. This kind of thing where I'd say, okay, well, at break time, I'll go in my office and I'll look in the solution manual and I'll see what one they did. Now, this isn't the most current solution manual, so if the same problem isn't in there. Matter of fact, pretty sure it's not going to be in this book. But bear with me for a second.
I see that the lines match up if you graph those two, but I know that's not a paper and pencil way.
Yeah, what I'm trying to do here, I just want to see what solution got reported. And it's not even the same problems. Okay, hold on. I have the book. No, it's somewhere. All right. So and we just did number 48. Okay, so the way they did it was the second way. So this is in the solution manual. So we have a bit of a interesting little thing here. So apparently the cotangent of x over 2 is the same as the cosecant of x plus the cotangent of x plus some constant. Because if two functions have the same derivative, mean value theorem tells us eventually that they just differ by a constant. So this is the kind of shit I used to do. Like after I'd do the integrals, if I saw that there was two different ways to do it, I'd do it both ways, you know. Okay. Another problem for you. Now this one is going to be kind of a interesting little catch to it. I want us to find the integral of 0 to 2 pi. Okay, now there's going to be more to this story. So I want to give you a second to work on it. Okay, now just think about those identities. It's the bounds. That's the interesting thing here. All right, well, what identity did you come up with here for this guy?
You say that 2 cosine squared x is equal to 1 plus cosine 2x?
Okay, that's way to good place to be. Solution here. Okay, so we start off with the basic identity, and this is how my memory works. I remember it like this. We're going to have 1 plus the cosine of 2x is equal to 2 cosine squared of x. So the integral is going to be 0 to 2 pi, the square root of 2 cosine squared x dx. Okay, now how many of you got 0 for your answer? Did anybody?
I do.
Yeah, okay. Now, this integral is going to come up again in a few weeks, okay? I'm doing it right now, and then it's going to come up again in a couple weeks. If I bring the square root of 2 thing out of here, and I get 0 to 2 pi, I have the square root of cosine squared x. Okay, now. Here's what y equals cosine x looks like. Goes like this from 0 to 2 pi, and it is negative from pi over 2 to 3 pi over 2. Okay, now for those of you that answered 0, I'm going to give you 60 more seconds to now rethink what happened and adjust. I think my son Trevor was over at his buddy Van's house, who has a cat. Because this is seriously like when I first started dating my wife and she had a cat at me in her apartment for 30 minutes. This is how I get. So what I did is she wasn't there. I killed the cat. I'm just kidding. I didn't kill the cat. When we moved in together, we gave the cat to her sister's boyfriend, Dave. And then they broke up. So whatever happened to that cat? All right, so here's the interesting part of this problem. The square root of something squared is the absolute value of the thing that's being squared. Okay? The square root of an unknown quantity squared is the absolute value of that unknown quantity. Now, how this is going to show up later, we'll be back in person by the time this happens, obviously. We're going to have a curve out in space, and it's going to look like this. And we're going to go try to figure out the length of the curve. And we're going to do some kind of an integral, and we're going to get 0 for the answer. And I'm going to go, okay, the length is 0. I remember one of the last times I did this, it was a smaller 185. I was covering for art upstairs, and I did that problem. I said, all right, so the length is 0. And they all, there's like 20 of them in there, so it's not a big room, Not one of them said anything. So I waited 5 minutes after I did another problem, and I go, hey, let's go back to this one. I just told you that the length of this curve is 0, yet I drew it. Look, it had ink left the pen. It can't be 0. Okay, so what we have to do in a situation like this, when we have bounds, is we're going to have to separate it up into where it's positive 0 to pi over 2 of cosine x dx, and then plus the square root of 2 from pi over 2 to 3 pi over 2 negative cosine x, because cosine is negative in this region right here, right? And then it's going dx. Hey, what time is it in Beijing right now? Anybody? Somebody?
1 second.
Probably like 3 in the morning.
3 in the morning.
2:32 a.m.
I think if you talk about the China hours, it's gonna be like 1:30.
2:30.
Yeah, 1:30. or
2:30.
whatever. No, 2, yeah. 1 to 2.
2:30 in the morning?
Mhm. Like they are like, I think like you just add 3 or 4 more hours. That's
Back when I was in high school, all of China was on the same time zone. So everywhere in China was always the same time. Is it the same way now?
Still is.
probably, yeah.
It's like a 16-hour difference between here and Beijing.
16 hours, okay. All right, well, here we go. So now we're ready to integrate this thing. So this is radical 2 times the sine of x, evaluated at 0, pi over 2, minus radical 2 sine x, pi over 2, 3 pi over 2, plus the square root of 2 times the sine of x, 3 pi over 2, 2 pi. Okay, so that's radical 2, 1 minus 0, minus radical 2 times negative 1 minus 1, plus radical 2 times 0 minus negative 1. So I got radical 2 plus 2 radical 2 plus radical 2 to get 4 radical 2. What do you think? Should I put this problem on the test?
Probably not.
I think so.
Okay, so that was a trick question. Of course, the answer should be yes. Why should the answer be yes?
Because it's an
We're gonna
absolute
learn this.
value. Because you
Because
just solved
I
it.
know how to do it. Right? I do this a lot. I will put problems on the test that I did, during class and made a big bold stink about it and all that stuff. Oh, we got some worker guy here. All right.
Okay.
Yeah, go ahead.
I have a question.
Oakley, shut up. Okay. Oh, hi. Go. Oh, okay. I feel hot nose. Yeah.
Take that, Oakley.
And Oakley was never heard from again.
I'll lock the dog up. What's your question?
Yeah. So I understood like everything that you did here, but can you scroll up just a little bit? All right, here. Why did you put cosine squared of x equals to half plus half cosine 2x?
That's an identity.
Oh, so 1 plus cosine to like square root of 1 plus cosine 2x becomes that, and then I solve for cosine.
Right.
Okay. Thank you.
Professor, are you saying that we can expect this problem on the test?
Saying I might put it on the test.
Is U by substitution, like substitution by U, possible here?
Well, what would you want to let U equal?
Cosine 2x.
Okay. So let's give that a try. So U equaling the cosine of 2x. Okay. Now what? We don't have a sine x to use in the du, right? Who's that? Where's Ox? Hopefully up.
Do you know where we can review the identities?
Yeah, in the appendix. And
I think it's Appendix D, at least in
Appendix
the
D.
edition.
Appendix D is the trick thing. Now, this is the kind of stuff that we're all expecting. We're going to be going back to in person, and whether or not you're figuring out a way to cheat on the test or not, we're all expecting you guys to do shitty, because most of you got an A in Math 180 and probably wouldn't have under normal circumstances. So we all know that you've got holes. All right. So this is why this semester is going to be a little different, when we go back, because it's not your fault that COVID happened. Okay, now try this one. See what you can come up with. Very similar to that one we just did. And if you want, you can go 0 to 2 pi or whatever. But I'll give that one a go. All right, well, let's start looking at some new stuff. Okay, now this is an entirely different type of substitution. And when some of you that have to go there get to Math 280, I have to kind of remind you on how this substitution is going to go. Okay, so here's the story of how I learned that the derivative of sine inverse was you guys remember this?
1 over square root of 1 minus x squared.
Right. Okay, so senior year in high school, I'm in calculus. we were not doing early transcendentals. All right, so that meant we didn't deal with the exponential function, the log function, and all of the inverse trig functions until basically towards the end of the year, you know, and we've all got senioritis, nobody's paying any attention. But I do remember scrambling, needing to learn this stuff. So what Mr. Plackmeyer did is he put a problem down on the board and he said, all right, let's see if we can figure out this antiderivative. And all we're going to be doing is symbolically manipulating. There's no bounds anywhere. Okay. So what he says, he looks at the domain of the function f of x, and he realizes, and he explains to us that the x's can run between -1 and 1. Can't have it equal to 1 or -1 because of division by 0, right? So Mr. Plackmeyer has this bold substitution. He said, okay, well, here's a function that takes its values between 0 and 1. I mean, -1 and 1. And so if we were to do this substitution, then dx d theta would be cosine of theta, leading us to dx is going to equal the cosine of theta times d theta. All right. So when we shove all of this stuff in, we arrive at the dx divided by this, which we can write as this. And this is exactly how this gets done at schools that use the non-early transcendental books. I don't see an advantage to that at all. Maybe attract more business majors. I don't know. Okay, now in the last problem, I made a big song and dance out of the square root of something squared is the absolute value. But here we're just symbolically manipulating. So there's no bounds here. And so all textbooks just dance around this idea. And if you start reading in our textbook, we get the integral of d theta, which is just going to be theta plus a constant. Now you start with x, you got to end with x. So since x was equal to the sine of theta, then it's understood that theta must be the sine inverse or the arc sine of x. And so our integral ended up equaling the sine inverse of x plus a constant c. And so this is how I was taught that derivative. And when I first started at Orange Coast College, during my first couple years there, we were 18-week semesters. And we had lots of committees that met about things and whatever. But the one committee that seemed to always have plenty of interest was the calculus committee, because people were very territorial about their courses. And anyways, we were not doing early transcendentals. And when we switched to the 16-week semester, I brought it up. So look up, guys, I'm doing Math 185. I've got to do all of that stuff. You could do Math 180 in 10 weeks because of the lack of material in there. So let's go to early transcendentals, and everybody agreed. Let's give this new kid a win in the win column.
He's coming back.
So, and I still think that there is material, like all of this stuff we're doing right now in chapter 7. We should have been doing at least half of it last semester in Math 180. All that horse shit about volumes of revolutions, and the only reason any of us cover that shit is because it's a section in the book. You know, if Andy and I ever went through in our threats to each other and wrote a textbook together, we're definitely leaving all of that stuff as exercises. You know, that whole section on work, that's inappropriate. Does not belong in a math book. Belongs in a physics book where you have an expert in physics delivering that material to you, not some knuckleheaded math person, you know, whatever. Anyways, so this is how I learned this thing. Okay, so this kind of leads to a type of substitution technique that maybe if we had a problem like this, where like that. All right, well, let's see here. If we want to take advantage of the identity that we used right here, we're going to have to make a small little adjustment. Okay, so what we want to have happen is for 4 minus x squared to equal 4 minus 4 sine squared x. So in order to get that, what do we need to do? We need to let x equal to sine x. Okay, sometimes these things get a little carried away, you know. And so it kind of helps to have a strategy like, okay, this is what we want. Let's back into what's needed to get that. Now, if you're going to make a mistake on these, it's always forgetting the dx part. And you'll even see me make the mistakes from time to time. Okay. All right. So when we plug all of this stuff in, our integral becomes the square root of 4 minus 4 sine squared x. Then dx is the 2 cosine of x dx. And downstairs we have a 4 sine squared x. All right, so now what's left for us to do is to clean all of this crap up. So that's going to be a 4 square root of cosine squared x cosine x dx over 4 sine squared x. Okay, so now we're just symbolically manipulating here, right? There's no bounds. So we're just going to end up with this over this. And that is the integral of cotan squared x dx. Okay. Good time to take a 60-second pause here. And I want you guys to think about what you're going to do next. Because if I just keep going, you'll just keep writing it down. And you might even think that, oh yeah, I thought of that idea. Yeah, he was reading my mind. Yeah, Bobby's psychic. He knows exactly what I'm thinking. What are you going to do here? Is the derivative of some basic trig function cotan squared?
No.
Didn't we work on this problem the other day? What would you do here?
Turn it into sine and cosine.
No, you would do this. See? See how easy this is? Okay. So what is the corresponding cotangent identity? Okay, now if you don't know, figure it out. Just write sine squared plus cosine squared is 1. Let's see, if I divide everything by sine squared, what we see is we have 1 plus cotangent squared of x equals cosecant squared x. So that means that the cotangent squared of x is the cosecant squared of x minus 1 dx. So the antiderivative of cosecant squared is negative cotangent of x. And oh boy, did I fuck this problem up. So that's got to be a theta. That's got to be a theta. All of these x's are now thetas.
Even the dx turns into a d theta.
Uh-huh. So I have to go back. Theta, theta. Theta. So all of this is theta. Theta, 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 So now this is theta, d theta. Negative cotangent of theta minus theta plus a constant c. Okay, now we have to go back to our substitution. So maybe one or two of you go clear back with me to pre-calculus. And if you do, back in those days, I would have said, all right, we need to draw a triangle that represents this substitution. So that means that the sine of theta is x over 2. So let's draw a triangle that has that in it. If whoops. Did I lose you guys?
Yep.
We
You there?
we
Okay.
hear you, but we don't see you or see the screen.
You don't see the screen? Okay, let me figure out what happened here. There's that. Let's try share the screen again. All right, see the screen now?
Yeah.
Yes, sir.
Yep, okay. So we draw a triangle that represents this substitution. So if this was the angle theta, the sine of this theta is x over 2. So this is going to be the square root of 4 minus x squared by the Pythagorean theorem. Now, notice that that's a part of the integram. This is a clue that you're doing it right. So anyway, what would the cotangent equal? The cotangent of this angle is going to be, well, the tangent of this angle is x over 2, So the cotangent of that angle would be 2 over x, right?
Professor, I think the hypotenuse is 2 since sine theta is x over 2, opposite over hypotenuse.
Oh yeah, screwed that up. Okay, so the cotangent of this theta is going to be negative, is going to be square root of 4 minus x squared over x minus theta, which is the sine inverse of x over 2. So there's a awful lot of stuff going on in that problem. Okay. All right. Let's try something of a slightly different flavor here.
I have a question.
Uh-huh.
So I have 2 questions. My first question is, can you scroll up just a little bit? All right. How do you, what, based on what did you decide that you want 4 minus 4 sine squared of x? And why did you decide that you need x equals sine theta, 2 sine theta?
Because I want to take advantage of this identity. If I just let x equal sine theta, I would have 4 minus sine squared theta, not 4 minus 4 sine squared theta.
And we decided what we needed.
You don't have to do it like that. You can just manually try to figure it out. Let's try this one here. So the integral of x cubed over the square root of x squared plus 4. So this time we want to take advantage of the identity that tan squared of theta plus 1 equals the secant of theta. So it looks like if we were to let x be 2,
Is it secant squared of theta? Or secant, yeah.
yeah. If we were to let x equal 2 tan theta, then x squared plus 4 would be 4 tan squared theta plus 4, which would be 4 times tan squared theta plus 1, which would be secant squared of theta. And then dx is going to be 2 secant squareds of theta. Okay. My wife and I watched that movie, The Power of the Dog. Did you guys watch that?
The power of the dog.
That movie was fucking stupid. And it's got Doctor Strange in it playing some weird cowboy. Done. So we shove all of this stuff in, and our integral becomes let's see, x squared is going to be 4 tan squareds of theta. The dx is the 2 secant squared of theta, d theta. And then down here, we're going to have the square root of 4 secant squared theta. Okay, now again, there are no bounds here. So we're okay. Let's say that that is the square root of secant squared is just secant of theta. Okay, so start cleaning this up here. We're going to have a 4 sitting outside. Then we're going to have a secant squared theta in the numerator. denominator, we're just gonna have the secant of theta. So that's gonna be 4 integrals of secant theta. Okay, now, again, under normal circumstances, you know, you'd be showing your work and whatever. But this is one of these integrals where I tell you what I would have told you 5 years ago before anybody heard of COVID. That this is one that you probably are eventually going to commit to memory. It's equal to 4 natural log of secant of theta plus tangent of theta plus constant c. Okay, start with x, end with x. Well, we had x equaling 2 times the tangent of theta. So that means that the tangent of theta is x over 2. Theta. Here's x over 2. Complete the story here. Okay, so the secant of theta the secant of theta, I believe, is going to be the hypotenuse over this guy. And the tangent of theta, that's just the x over 2 plus constant c. And I don't think there's much more you could do with that one. So that's probably where it is. Okay. Another one for you guys to try here. Here you go. And hold on. Getting a message here. Okay. I need to be at my office at noon. The tech person, Jake, the tech person is going to be there. Someone just told me. Okay, so what time is it? 11:15. All right, so we got to end this in about 20 minutes. All right, so you guys think about this one for 60 seconds, and then I'll jump in and do it. But I want you guys to get ideas going. Now, when we're in class, if we're in person and this is going to according to plan, this turns into a big circus, because I just say, okay, do this one. And then depending on the kind of room I have, like if you guys are talkers, and you guys do seem like talkers, you guys will start, no, do this, no, do this. And I'll just sit there for a minute or two. And then I'll say, all right, here's how to do it. But quite often, one of you figures it out and then shares. And that's really what I'm after. I want you guys talking with each other about this stuff. You really start to understand something. You have to explain it to someone else. Trust me. There's a breeze strip. Maybe I can. Oh, there's that one.
So do we just start talking?
What's up?
Do we just start talking to each other?
Well, you will. You will next week.
Oh,
But right now, I just want you to just jot some ideas down. If you want to share in the chat what you think to do or something, but that's kind of the way it's going to be in person. Okay, what kind of substitution did you guys come up with?
x is equal to 3 sine of theta.
Okay, so if we were to let x be 3 sine of theta, then we're going to have 9 sine squared minus 1. What if we were to let x equal 3 secants of theta? Then x squared minus 9 would be 9 secant squared theta minus 9, which would be 9 secant squared minus 1, which would be tan squared theta. And so dx would therefore be 3 secant theta tan theta d theta.
Professor,
Yep.
can I ask a question?
Uh-huh.
Like, I understand when you're like manipulating and solving, but what I'm not getting is why are you finding like x equals 3 sine theta? Like, based on what are you deciding it
No,
what to be?
I
Yeah,
didn't use that one.
or 3 secant theta. Like, what's the thought process here?
The thought process is this. I want to take advantage of this identity that the tan squared of x plus 1 is secant squared x, or tan squared x equals secant squared x minus 1. Now, if you read the text, he goes through all kinds of different cases. If you see this, do this. If you see this, do that.
Mm-hmm.
But anyways, it's going to take you several problems to do. You're not going to get good at this just by watching me do problems. I'll probably do 2 more and call it a day. You have to get in there and do them. And then on Thursday, go, hey, I couldn't do this one. Can you do this one? I couldn't do this one. But you have to spend time with them, scratching your head, failing. Failing is a big part of this process, guys. Unfortunately, you learn a lot from your failures. Like, for example, this was our first little attempt here. That was not a waste of time because we learned that that wasn't the best approach. This approach was more direct, and it's giving us x squared minus 9, which is 9 tan squareds of theta. The dx is a 3 secant theta tan theta d theta. And then downstairs, we're gonna have, looks like 27 secant cubes of theta. Okay, so there's gonna be a 9 in the top, so a 1/3 is gonna live. And then there's going to be a tan squared theta over secant squared theta d theta. That's what it looks like to me. And we turn this into sines and cosines. Some of you don't need to do this step, but let's just do it. 1 over secant squared is cosine squared. And so what we're left with is the integral of sine squared theta, which we use that identity I'm already seeing the disconnect, but I didn't see it last semester. My strategy is usually teach pre-calc and calc 1 in the fall, calc 1 and calc 2 in the spring. And that's exactly what I did this year. Last year I did the same thing, and I definitely saw it in Math 185. You know, now most everybody got everything correct on the test because everybody arranged the Discord accordingly and figured out how to, you know, post answers. But as the semester went on, I mean, I had people dropping out of the class because they knew they would get 100% on the test, but they had no clue what the hell I was talking about. And it's just because the previous semester, not learning the basics of Calc 1, you know? So some of you are going to have a bit of a struggle with this. We all recognize this. More so than in just normal semesters. Like sometimes, you know, you come from Calc 1 and you had a retired on active duty person. And we've had people like that in the department that we had a person in the department that used to teach intermediate algebra to large lectures, 140 students. And this particular person decided it wasn't worth the time to cover logarithms. And I remember having a bunch of college algebra people saying this one semester, this is like over 10 years ago, saying, all right, so we're going to review logarithms right now. And I had like a third of the class going, what? And this Italian woman in the class with a real thick Italian accent. And, you know, she's one of those, like, her kid is old enough to where now she can go back to school and she is put together, you know, she would leave my class and go volunteer in her daughter's classroom. I guess she was in second grade or something like that. But this woman was a good student. She was, you know, organized, and she even helped organize everyone else. Because, you know, we were doing our, you know, part 1, part 2 stuff even back then. And she said, I had so-and-so and we never covered this. And I trusted her, you know, because she's a good student. So this even happens from time to time in regular semesters. Anyways, we integrate this and we're going to get theta over 2 minus 1 over 4, the sine of 2 theta. Okay, so this is going to be 1 over 6 theta minus 1 over 12, the sine of 2 theta. Okay, now the substitution that we made was that x was equal to 3 secants of theta. So if we draw the triangle, the secant of theta is x over 3. And so this would be x squared minus 9. Okay, now here is where we have an issue. I don't have theta, I've got 2 theta. So we need to use an identity here. 1/6 theta is the secant inverse of x over 3, right? Okay. And then minus 1 over 12 times 2 sine theta cosine theta. So now we just use the triangle again. Minus 6, the sine of theta is this number over that. The cosine of theta is 3 over x. So I guess if you wanted to wrap it all up in a,
Is it 1/6 on the second term?
yeah, 1 over 6. X over 3 minus, then it's going to be the square root of x squared minus 9 over 2x squared.
So I had a question.
Uh-huh.
So when you go back and you put the thetas and you go back and get the x for the final answer, to figure that out, you used your substitution and then basically SOHCAHTOA and you drew a triangle.
Yeah.
And that's how you know how to put in to substitute back in to get the final answer.
Right. So we have that since x is equal to 3 secant theta, the secant of theta is x over 3. Okay, so you just draw a triangle, a right triangle that has that in it. Now there's other ways to do it. You know, we could have said, you know, the triangle would look like this. We could have said x over 3 and then a 1 down here, but then this becomes a big mess over here. All right, well, let's see here. What happens when this stuff starts to get a little bit on the messy side? Like, how about this thing? For example, the integral of x squared over the square root of 3 minus 4x squared dx. Okay, now there's a couple different ways I've seen people approach this, maybe 3 or 4 ways as a matter of fact. Depending on what those coefficient numbers are, the 3 and the 4, like if one of them is a 1, I might handle the problem a little differently, depending on where it is. So what I'm going to do Because I'm just gonna start playing around with this. 3 minus 4x squared. And I know that x is gonna be something times the sine of theta, because I've got a number minus x squared. Okay, so the question is, what is it that I'm gonna put there? So the way I do these is I'll factor the 3 out and get 1 minus 4 over 3 x squared. Okay. And so what I want, again, if I put this down, if I want 1 minus 4x squared over 3 to be 1 minus sine squared theta, what I would need to get this to work would be to have 2x over the square root of 3 equaling sine of theta. Or x equals radical 3 over 2 sine of theta. Now we could also maybe factor the 4 out, and this is for you to do on your own. I would say, it's 11:30, we'd be, towards the end of class. I always try to, when we're back in person, by the way, I always try to end at no later than a quarter till, because usually you guys have a bunch of homework questions you want to ask me, yet you got to get across campus to your next class, or you got something you got to get to work, and you weren't able to make it into my office hours in the morning. So I always try to do that. Now, this past 2 years have been kind of lecturing, unless I had something to do. Like today, I got to go over there and meet the person to show them what to fix. We have a very skeleton crew. People were retiring, leaving, getting new jobs. There wasn't as much work for like the custodial staff, and so they started leaving and getting better jobs or whatever. And then when we started talking about coming back, everybody was like, well, hold on a second. There's only 2 campus safety officers. We can't have all. I think at any given time, I think it's somebody said 6,000 people on campus or whatever. I don't know. So now we just start filling all this stuff in. Dx is going to be radical 3 over 2 cosine theta d theta. This is going to be a mess, so try not to worry about it. It is going to be a mess. So x squared is 3 over 4 sine squared of theta. Dx is radical 3 over 2 cosine of theta d theta. And downstairs, I have 3 minus 4x squared well, how about I just put it in there? 3 minus 4 times radical, no, squared. There's the 4, and then here's the 3 over the 4 sine squared theta. Okay, so let's start cleaning this up here. I'm gonna get 3 radical 3 over 8 sine squared theta cosine theta d theta divided by 3 times 1 minus sine squared theta. Okay, so now I have 3 radical 3 divided by 8, and now I have another radical 3. We have sine squared theta cosine theta d theta divided by cosine of theta. And so once again, we end up with the sine squared integral. So that's going to be 3/8. And how about I just cut to the chase? 1/2 theta minus 1/4 the cosine, whoops, the sine of 2 theta. Okay, so that's what I'm doing. Sine of 2 theta. And let's see, this is going to be 3/16 theta minus 1/2 the sine of theta, the cosine of theta. Okay, now, way back up here, the sine of theta was equal to 2x over the square root of 3. So 2x over the square root of 3. So that means this side has to be 9 minus 4x squared, right? And is that
Isn't it 3 minus
3
4x squared?
3? So 3/16 sine inverse of 2x over radical 3, and then minus 1/2 the sine of theta times the cosine of theta. And if you want to clean that up, you know, you can. 3/16 sine inverse of 2x over radical 3 minus, looks like x radical 3 minus 4x squared over 3. And there you go. Okay, now the older textbooks have more exercises in them. So when you run out of things in Stewart to do, just go somewhere else. You know, your job right now is to integrate. You know, take integrals to work with you when you got nothing better to do. Okay. Any questions on this one?
Is this on the textbook so I can read it over?
There's several examples in the book that are similar to this. I'm using convenient numbers, you know. Okay, now as a little parting shot here, before we hang up, and I should probably get in my truck and get over there. He's got one in here where, well, he's got more than one, but let me just show you how to do this one. Okay, so what we want you to do here is to complete the square, meaning write it as x squared plus 2x plus 1 plus 4 to get it to dx over the square root of x plus 1 squared plus 4. And then if you were to let u equal x plus 1, du would just be dx. And so you then proceed with this guy. And go. You're gonna let u be 2 tangent. Okay, well, 7.3, unfortunately, he only has 44 exercises, and some of them have calculators next to them. Exercise number 39. I just watched an interesting video on YouTube on what Isaac Newton did in order to get better estimates of the number pi. But anyway. So on Thursday, I might be broadcasting to you guys from the classroom. I'm going to try to simulate where I have it up on the projectors, you know, and there we go. Okay, now I haven't dropped anyone from this class. If you're a pre-calculus teacher, only covered half the material. Yeah, a lot of depends on your school district too. All right, guys, I'm gonna get over there and try to get him to. I'm gonna get all the way over there, and the guy's gonna be late. Watch. So it always is. And then later on this afternoon, if you want to see me, I'll probably be over at the baseball field. We have a game at 1, so I usually show up around the 5th inning or something like that. All right, guys, I will see you on Thursday or maybe at the ballpark today.
Thank you,
Thank you.
Professor.
Thank you,
Professor.
Professor.